So this is day 2 of lesson 7-1. We already talked about greatest common factor and how you find and prime numbers and divisibility rules. And so we really looked at greatest common factor of just numbers with no variables. So today we're going to add variables to the mix and see where we go from there. So we have example 1, and we are going to do the same thing that we did yesterday, except we'll talk about the variables towards the end. So let's start with prime factoring our numbers just like we did yesterday. So we're going to take 15 and break it down into whatever multiplies to give you 15. In this case, you have one choice, 3 and 5, both of which are prime. So we're going to circle those. And then for 51, a lot of you think 51 is prime, but start going through your divisibility rules. You can either think about the fact that you know what divides into 15. You came up with 3 and 5. So if they have a greatest common factor, 51 would be divisible by 3 or by 5 or by 15. But if you choose 3 and 5, and both of those go in there, then you know 15 also goes in there. So the rule for 5 would be that the number ends in 0 or 5. Since 51 does not end in 0 or 5, we know that 5 doesn't go in there, so therefore 15 can't either. And so that leaves us with 3. So the rule for 3 means you're going to take 5 plus 1, so add up the digits. That gives you 6. If 6 is divisible by 3, which it is, so is 51. So I know that 3 goes into 51, and if you divide or use your calculator, it goes in there 17 times, and both 3 and 17 are prime. So we are going to list out 15. Its primes are 3 and 5. And we're going to list out 51, and its primes are 3 and 7. So I can line up the 3 with the 15's 3, but the 17, I said 7, I meant 17, cannot line up with a 5, so we have to give 17 its own column. Then let's talk about the variables. So 15 has x to the 5th, which means we have 5 x's. So this is the only example that I'm going to stretch out the variables, and then we're going to talk about a shortcut. So I'm going to stretch out all 5 x's. So I've got x, 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 and x. So there's 5 x's for that x to the 5th, and then we have a y, so times 1y. The 51 has x squared, which is 2 x's. So you can line up those 2 x's anywhere underneath the 15's 5 x's. Again, I like to choose to line them up at the end. So there's the 2 x's for the 51. And then 51 also has 3 y's, so I can line up one of its y's underneath the 15's y, and the other 2 y's will have to have their own column. So then draw a line. And then we're going to do the greatest common factor exactly the same as we did yesterday. We're going to circle what they have in common. They both have 1 3 in common, and they have an x, a second x, and a y. So drop down one of those from each of the columns. And then multiply them together. 3 times x times y is 3x squared for the 2 x's times the y. So our greatest common factor is 3x squared y. So let's talk about a much simpler approach than having to stretch these variables out every time. So when we talked about greatest common factor, it was the biggest number that divided into 15 and 51. So in our case, it happens to be 3. 3 is the biggest number we can divide into each of these. When we divide 3 into 15, we're going to be left over with 5. Divide 3 into 51, we'll have 17 left over. So you kind of think about the same way with variables, only ask yourself the following question. How many x's can I take away from each of these terms and take the same amount away? So a lot of you are going to say 5 x's or 3 x's or, whatever, but I can take 5 x's from this one because it has 5 x's to take. But can I take 5 x's from this one? No. So at most I can take 2 x's from this one. So that's a restriction right there. I can only take 2 x's from this one. I can't take 5 like that one has. I can't take 3 because that still only has 2 x's. So the most x's I can take away from both of them and take the same amount is 2 x's, because this one is restricting the amount that we can take away. So you always look at the smallest exponent for your variables, and that's what you're going to take. So as I'm looking at these two, x squared is the smallest, so that's going to be in my my GCF. And then for the y's, how many y's can you take away from both of them and take the same amount? This has the smallest y's, that doesn't. So I can take 1 y from this and 1 y from this and still take the same amount. I could take 3 y's from this one, but I don't have 3 y's to take from this one. So I can't take 3 y's from both of them and take the same amount, or from each of them. So I can only take 1 y from this one and 1 y from that one to take the same amount. So that's how we ended up with 1 y in our GCF. So let's move on to example 2 and apply that concept without stretching out the variables. So again, if you can look at 27 and 45 and know what the biggest number is that you can divide into both of them, then you can skip what we're going to do. So I'm going to go ahead and prime factor 27. You only have one choice, and that's 3 and 9. And so I'm going to circle 3, it's prime, but 9's not, because it can be broken into 3 times 3. And circle those. 45, I'm going to use 5 times 9. You could have used 3 and 15, but I like 5 and 9. 5 is prime, so we're going to circle 5. And 9 is 3 and 3. And those are also prime. So if you stretch out 27, I have 3 times 3 times 3. If you stretch out 45, I can line up my 2 3's underneath the 27's 3's, and the 5 has to have a column of its own. Draw a line. GCF equals, circle what they have in common, which is 2 sets of 3's, bring them down 1 3 from each group, and multiply, and we get 9. Now if you had seen the 9 right away, then you could have skipped all this and just said, oh, I know I can divide them both by 9. Just make sure that you have the largest number that you're dividing into. Now we're going to add on to this. I'm going to back off that square I just put around the 9, because we still need to add on our variables, right? So look at our variables. So we've got A's and B's. So let's start alphabetically. Makes sense. We've got 2 A's here and 3 A's here. How many A's can you take away from both of these and take the same amount? Well, it can't be 3, because I can't take 3 2's away from an A squared. It only has 2 to give. I can take 3 here, but I can't take 3 here. So I can only take at most 2 here. So that means I can only take 2 here. So the most I can take from each of them and take the same amount would be a to the second. Now as far as your b's go, I have no b's here and I have b squared here. So the most b's I can take away from both of them and take the same amount is none, because although this has 2 b's to give, this has no b's to give at all. They have no b's in common at all. So we cannot include b in our GCF because it is not a common variable that they have. They only have a's in common. So that's it, 9a squared. All right, so example 3 has 3 terms in it, which again is not a big deal. You're just going to look at 8, 4, and 12, and those are small enough numbers that you could probably think to yourself, what could I divide them all by and divide by the same number? So the smallest number is 4. So that means that that would be the biggest number that would be possible, because this smallest number is always going to be our restrictive value. So can you divide 4 into 8? Yes. Can you divide 4 into 12? Yes. My guess is that 4 is going to end up being our greatest common factor as far as our numbers go. So let's just quickly do that so I can prove it to you. So if I prime factor the 8, I'm going to use 2 and 4. Circle your 2, and the 4 becomes 2 and 2. So then I'm going to stretch those out. And then the 4 is 2 and 2. So I'm going to stretch those out. And then the 12 is 3 times 4. You could have used 2 and 6, but I like 3 and 4. And so then for 12, we're going to line up the 2 2's here. And then the 3 has to have its own column. Draw a line. GCF. We've got these 2's in common. So we're going to drop down a 2 from each of those. And sure enough, when we multiply, don't we get 4? And that's kind of what we thought, just looking at the biggest number that divides into all of those. You always have to look at the smallest number, and your GCF cannot be bigger than that smallest number. It's just not possible. So now look at your A's. So as we look at the A's, the 8 has 4 A's, the 4 has 3 A's, and the 12 has 2 A's. So this is the smallest number of A's. So at most, and they all have A's, so at most we can take 2 A's from each of these and take the same amount. Notice that this has 4 A's. I could take 4 from this one, but this one doesn't have 4 to give, and this one doesn't have 4 to give. The most that each of them has to give, and to give the same amount, I'd be taking 2 A's from this, 2 A's from this, and 2 A's from that, would be A squared. So as far as our A's go, goodness. Okay, so A squared there, that's much better. And then as far as our B's go, this has 3 B's, 3 B's, 3 B's. So all of their B's are identical. Got 3 B's each, so I could take 3 B's from this, I could take 3 B's from that, and I could take 3 B's from that. So the fact that they all have the same amount of B's means that I can take a B cubed from each one of them and take the same amount. So my GCF is 4A squared B cubed. Now let's look at an EOC style question. So let's look at the next page. Okay, so I don't know what I did with page 2. So I just really shrunk the first page here, so ignore that. This is page 2. And it's an EOC style question. And so bear with me, we're going to read through this. It says a cafeteria has 18 cartons of milk. And so typically, as I read a word problem, I'm going to circle important things. So we have 18 cartons of chocolate milk. And then we also have 24 cartons of regular milk. The cook wants to arrange the cartons with the same number of cartons in each row. Well, that would be important right there. The same number of cartons in each row. Chocolate and regular milk will not be in the same row. So we're going to have a row of chocolate, a row of regular, a row of chocolate, row of regular, however he wants to do it. But each row has only one type of milk in it. How many rows will there be if the cook puts the greatest possible number of cartons in each row? That's GCF. So as you're reading this, anytime you see greatest possible and you're arranging things, that's one thing that we can use greatest common factor for in real life. So as I'm looking at my chocolate milk, I'm going to split it up this way. So I'm going to start with chocolate milk. So step. So then, when we go to page